young students. For me, you are all students, even if you are professor. So first talk will be by Neha. Am I right, Neha? So she will give a talk. So माइक लगाना है उसको लगाइए, हमको मत लगाइए. How many minutes late?
Ramji Prasad sir, Dr. Devendra Singh Gurjar sir, and everyone. So the topic of my presentation is hybrid FSO RF systems for 6G. Free space optics. Free space optics is also known as the optical wireless communication. In this, the visible light or the infrared light is used to transmit the data. It is for the short to the medium point-to-point communication. The main primary principle for the FSO communication is it requires the line of sight path. Some of the advantages for the FSO communication is security, high data rate, immunity to the electromagnetic interference, unlicensed spectrum, low cost, and it is easy to install. But there are also many challenges in the FSO system, such as it is highly affected by the atmospheric turbulences, attenuation. If there is any obstacle in between the transmitter or the receiver side, then it is unable to communicate. Wavelength and the molecular absorption. As the FSO system is highly affected by the atmospheric conditions. So the main wavelength range is for the FSO system is 700 to 1600 nanometer. From the table we can see that the wavelength 690 and the 1550 has the lowest molecular absorption. So among these two, 1550 is considered to be the best because it has the low absorption as well as it is safe for the human eye. Some of the applications based on the different wavelengths for the FSO system are like for the inter-satellite communication, it is 830 and the 1064 nm wavelength. So on for the deep space communication, it is 1064 and 1076 nm. Similarly for the UAV to the ground link, it is 1550 nm. Radio frequency. Radio frequency utilizes the electromagnetic waves in the radio frequency spectrum range for the data transmission. It has the high coverage and it is hardly affected by the obstacle in between the transmitter or the receiver. Here from the figure you can observe there are the different frequency ranges based application. Such as for the marine communication, the frequency ranges from 3 kHz to the 30 kHz. So on for, we can see for the satellite communication, it is 3 GHz to 30 GHz and so on. So here is a small comparison between the FSO and the RF. When we see for the device sizes, FSO has the smaller device size as comparative to the RF, whereas the power consumption for the FSO is low and for RF it is moderate. FSO is highly affected by the environmental parameters, whereas the RF is affected by the interference multipath fading. Path loss is high for both of the links. Bandwidth is higher for FSO and lower for the RF signal, whereas the speed for the FSO is high and for the RF it is low. Security is higher in FSO communication and lower for the RF communication. Data rate is higher for FSO and lower for the RF signal. And EM interferences, there is no EM interference for the FSO system, but it is present in the RF system. So we have seen both the advantages and disadvantages of the FSO and the RF communication. So we can consider a hybrid system which include both RF and FSO, considering their limitations. So these systems helps us to mitigate the signal interference and the weather related disturbances. Also it enhances the availability and the reliability under the severe weather condition. Here how these hybrid system works. If we are considering both the networks simultaneously, we can use both the networks for transmitting the data. Second one is we can access one of the best network among both of them. Third one is we use one link for forwarding the data and other one link for the return path. And most commonly we are using the fourth method, that is the top priority network, and keeping another one as the backup. Here are some advantages for the hybrid system. It enhances the reliability of the communication system, increase the security, data rate also increases, and reduce the latency, which are the key features for our upcoming 6G communication. But there are also the challenges, that is the synchronization, handover management, careful design, and the regular monitoring is required. So I have taken one of the example to showing how these hybrid systems are better while using alone RF or the FSO, and reference is also mentioned there. See, from the table, if we consider a snowfall weather condition, RF is available, whereas the FSO has 39.49% of availability. So if we are using the hybrid, we have the 100% of the communication. Same goes for the dense forest, where the FSO has only dense fog, where FSO has only 0.51% of availability. And for the rainy situation, it is 14.29 for RF and 85.71% for FSO. So the hybrid communication has 85.71%. So when we are using this hybrid communication, there is a trade-off between selecting the suitable frequencies for these hybrid setups. Desired data rate and cost requirement would also play an important role for selecting which one may play the backup or which one can be our primary link. So the techniques which we can include in this hybrid system are adaptive link switching, RIS systems, machine learning based channel prediction. We can predict which link is useful, which link we can use at a time, or the optical wireless networks and the terahertz communication. Here are some of the applications of the hybrid system. It can be utilized in the V2N communication, ground to satellite communication, underwater communication, military scenarios, UAV based communication. So the future research may include the adaptive link switching, quantum security, which is the feature of also the 6G communication, green communication, and the improved atmospheric models, that is using the better mathematical or the computational techniques to mitigating all these environmental factors. So the summary of the whole of the presentation is hybrid FSO RF is a key enabler for reliable and the high speed 6G networks. AI, RIS, terahertz integration may also involved. Research is going on for enhancing the efficiency, security, and scalability. Thank you.
Any question to Neha? Please ask at least 5 questions, one by one. At least you could take the lead.
Okay, Neha, you mentioned some of the advantages of FSO communication, right? So we know that there is some issues with the FSO communication, like this atmospheric induced bidding can actually disturb the performance. So what do you want to say about that?
Sir, there are various fading models we are getting to reduce this atmospheric turbulence induced in the FSO communication. So we can able to decrease it also.
Any more question? 5 questions. There is only 1 question. 4 more questions. Otherwise, you have to ask 4 questions. So, question.
So you have mentioned some challenges also. So like one of the challenge was handing over when we are using hybrid. So how you hand over? Like what are the problems in handing over?
As there are the 2 links, one is the RF and one is the. We are trying to use the switching methods like hard switching or the soft switching, but still sometimes transition from the RF to the FSO may get the problem. But we are dealing with it, and most of the techniques are coming for this. But currently we are using the hard switching and the soft switching for this management.
Hard switching means like sudden switchings.
Yeah, so mainly based on the signal quality or the SNR ratios, and also soft switching in which we transmit the data from both the links according to the communication requirement.
Thank you.
Third question.
Sir, 3 because I asked you questions.
Go to the heart.
Space of probably around 300 or sub 300 gigahertz band, and your RF probably will be a little bit lesser. So if you have to work on a device that will be able to switch between these two communication in a very wider bandwidth. So how do you think that designing of those devices which will be working on say 60 gigahertz to switching from 300 gigahertz? Probably something like that I can understand. You are using 60 gigahertz millimeter wave communication probably, and then you are going for 300 gigahertz or beyond.
As according to me, as the transmitter, and we are already using the two transceivers based on, one is based on the RF and another one is based on the FSO communication. So when we have the we are using the FSO as the primary. So when
Actually, you can answer in that way. Since we have two systems, RF system and FSO system, so we can design both transmitter and receiver as separate transmitter and receiver. So there is no problem like what you mentioned. I think you were asking like if you design a system which can transmit FR1 and FR2 bands, that will make the complexity much higher. But here in this case, I think she is talking about two separate receivers. Yeah. One is FSO, which will be having different set of equipments, and one is RF. So yeah. Switching, yes. Switching is required when we use one and we keep one as idle.
Okay, last question.
In case of rain, I guess the efficiency was 84 and 85%. Is there any way of integrating some other technology to get 100% efficiency or something like that? Because 84% is, I think, is less, because in 6G we are talking about ultra reliable. So it has to be above 98, 99. So how can we mitigate that?
we are working on it, that's why it's a future research. So we can get more and more.
Very good. Any question? Nobody. Okay, thank you very much. Thanks for putting hard in this also. This is really very good presentation. I give you 110 by 100. Second call है भाई बेटा. PhD student.
Yes.
Neha is also PhD student.
They all are my juniors. Neha and Partha are my juniors.
So your presentation should be better.
Much better.
Much better.
And who's your professor? He.
Then we just
Then he should also at the end he should give a presentation. That should be the best.
Start.
So first of all, I would like to welcome Mr. Ramji sir to be like to make ourselves like very proud to be in his guidance. Then I would like to thank the professors, and I would like to start my presentation on intelligent reflecting surface aided wireless network, which is actually emerging techniques for the beyond 5G communications. And first of all, I would like to start with the era of the 5G, which was actually released by the 3G BP, the third generation partnership program, in June 2018, which was released under in July 16, 2020, and the reference for that is given below. You can access the link, and you can go through the more details for that. And there several techniques were evolved, such as the machine type communications, then ultra reliable low latency communications, and then the EMBB enhanced mobile broadband communication. And for implementing these techniques, several emerging 5G paradigms, such as the massive MIMO, then NOMA technique, and OPM, all were integrated to form these to integrate themselves and to move towards the vision of for 5G wireless communications, which can offer the following applications, such as the multi-sensory augmented reality applications, which are applicable in the medical sciences, then for the gaming, then connected robotics and automation systems. Similarly, for this, the several driving trends are the reliability itself. Then it should offer a spectral efficiency. Then it should also offer the connectivity, massive connectivity to various IoT devices, which are actually located in diverse and vast locations. Then and also they have to be integrated with each other, and they could offer the efficient communication with the users. And the various enabling techniques for the 6G communications are actually they can be the mobile edge computing, which offers the computing at the edge itself. Then the massive machine type communications, which integrates the larger number of and vast number of the machine type, the IoT devices, then the very sensory nodes, and for them. However, implementing these techniques offer the basic challenges, which is the challenge itself, which is the propagating medium for the wireless communications. If we talk about, so this propagating medium, it actually it is the channel between the transmitter and the receiver, and it actually goes through a lot of fading problems such as the path loss, shadowing, and this can be shown in the figure itself. What are the possible solutions for them? So the three basic problems are that first, implement more number of base stations, which are actually sometimes not feasible in locations, especially in the remote locations, like such as the different terrains or mountains or oil rig applications, where the base stations cannot be implemented, and that has to be deployed in some distant locations. So for them, we can employ the conventional relays. Even we can have the unmanned aerial vehicles that can be utilized as the relaying operations. But however, they also have some drawback related to the energy constraints and the latency. And usually they operate under two different protocols. One is the amplify and forward and decode and forward. So the problem with the amplify and forward protocols for the relay is that they actually amplify the noise itself, so that reduces the signal to noise ratio and degrades the performance. And the other is the decode and forward protocol of the UAVs, which actually requires the complex circuitry on the UAV itself, which actually makes the UAVs more bulky, and which requires higher battery powers to power them, which again limits their operational time or the flight duration. Then the next is the new building materials, which are again, it's very difficult to break the whole world and build it with the new material. So that's also not very much feasible or not a right direction for. So in this direction, the intelligent reconfigurable surface has been become a prominent contender for this future generation wireless communications. And so what are these IRS? They're made of different patches, which are just essentially elements, and these are actually made from different PIN diodes, which offers different capacitor values, which changes the capacitances, and they can tune themselves in order to change their directions of the signal, the propagated signal, as shown in the figure here. A single as shown in the figure, here we have the n number of elements, where one element is shown in here, which can be made from which actually operates as a diode, which is made from the PIN diode, and then it is having most considered we actually prefer that it is a passive device. However, the research has been going on for the active devices also. But since we are moving towards an energy efficient and less power consuming device, so the passive nature of this has been more preferred over the active devices. However, the passive nature of these elements also imposes several drawbacks, which we will discuss in the later slides. So here, as you can see, there is a transmitter which needs to communicate with the two of the users, the user 1 and the user 2. And so here this RIS can be utilized as a reconfigurable channel, and it can go through the analog beamforming, and by using this analog beamforming, what it can do, it can beamform the signal to either user 2 or user 1 itself. And this beamforming can be also like in two different it can be also in two different ways. One, if user 1 is your intended user, whereas user 2 it can be your unintended user, or it is a node which haven't got a token key, so it can act as a passive eavesdropper also. We can consider it as a passive eavesdropper also. So this RIS can configure itself so that it can nullify the signal, and it avoids any signal to move towards our user 2. So it can also be a possible application of this RIS. Then from the previous slide itself, we can go through this. Where there is a transmitter which is communicating to the receiver with the help of the RIS having the n elements, and in the below it shows the matrix where there is a direct link from a transmitter to the receiver, which actually shows, and that the channel which is shown with the channel of H D BBT, which is shown here. And whereas from the different elements, like from the X is the channel is the transmitted signal from the transmitter, and this is the channel matrix from the transmitter to the element of the RIS, where this is the channel from the receiver from the RIS to the receiver, whereas this is your from the element 2 from element n. This denotes actually the reflection matrices of the RIS, which actually can be configured for the RIS, and actually that can be optimized for our improvement of our performance. Then to illustrate the operation, a simple scenario of an IRS assisted wireless network is shown in the figure, where we can see that the base station is having m number of antennas, and we have the IRS with n elements, and there are key users which are to be assisted by the base station, and there is the link between the base station and the user is actually very shadowed, or is very faded. So as already told here, from this element 1, element 2, element n in the center, they can be controlled by the reflection coefficients, which are actually shown by phi. So phi is actually an n cross n matrix, and this phi k is actually denoted by a diagonal matrix, which is shown below. So the received signal from the IRS to the kth user is given by equation 1, where we can see that it is having two components. The first component is the direct link, where your base station is having a direct link with your user. That can be denoted by the direct link of the channel matrix, and this X is actually a composite transmits data symbol, which is
use laser. Just press the center. Yes.
This one. Yes. So this component is actually the direct link, and here we can see this X. What is this X? So this X is actually the composite transmit data symbol, which is expressed as equation number 2, which is the summation form of the signal SK, which is SK is the unit symbol transmitted from the base station, and this WK is the weight vector, which actually comes from the digital beamforming vector, and it can be derived from the basic concepts of the beamforming. You can go through that. Actually, it's a very interesting topic also. And then the second component, which is actually IRS edit link, which have three subcomponents. One is the link. This is the link from the base station to the user. Then this phi of H. This is actually your reflection coefficient, which can be controlled and can be optimized. Then this G of X is your again your X is your simple, and the G is your gain, and this NK is your noise, which is actually additive word Gaussian noise. And one benefit of this RAS is that it removes, once your signal is received at the element of at the nth element of your RIS, so it can eliminate that noise signal. So once it is transmitting, retransmitting the signal to your receiver, your noise is completely eliminated. So that's one of the benefit of this RIS. And so in the equation number 3, similarly, we can obtain the received signal at the receiver, where again this component shows you this is your direct link and this is your indirect link, and based upon this YK is your received signal, and this received signal can be used to obtain your performance matrices, like for your if you are moving towards the reliability, so you can get the data rates and bit error rate and other performance matrices can be obtained by using these signals. So what are the different application scenarios? For this, actually, I have included some references where so the first from the Dr. Yuan, he actually considers a simplistic scenario which we have already discussed, where a base station needs to be transmitted with the multiple users, and in this scenario they haven't actually the direct link from the receiver to from the base station to the user. Then in the second scenario, where they have this access point, which can be used as a D2D communications also, considered as a D2D communications, where this device actually utilizes an IRS to improve the coverage and the signal strength. However, already there is a direct link between the access point and the user. Then the next application is it can be used to improve the physical layer security. So in the first scenario, Dr. Zhang actually he implemented an access point where there is a direct link from the access point and the eavesdropper and the user itself. So here the RIS can be used to nullify the signal, so that the signal which is transmitted through the IRS link, it actually counters or it actually nullifies the signal which is actually here transmitted from the access point to the eavesdropper. So this signal can be nullified, and the signal received at the user, it actually have the multiple copies of the received signal. Then in the second case, this is a simple case where the transmitter is not having a direct link with neither with the legitimate receiver and neither with the eavesdropper. So here the transmitter is actually using the IRS to make the communication link. So what are the different challenges in the IRS-based systems which actually offers the open research areas to you, and you can explore them? So first of all, is the channel estimation. As we already discussed, that here we are discussing about the passive IRS. So the channel estimation is actually very difficult. For them, we can have these active elements also. Like if we, for example, if we have n number of elements, so some of the m elements can be your active device that can be used for obtaining the estimations. And there are some other techniques also that you can go through in the literature. Then the second is the interference management. It actually occurs when there is a case of massive MIMO, where there are large number of antennas present at the base station, which needs to be transmitted with the m number of or k number of users. So there it can have a lot of interference or intercept interference also. So it needs to be managed before implementing the massive MIMO with the IRS. Then there is a hardware and power consumption. As I told you, if we are going towards an active RIS, so it needs to be we have to make sure that the power consumption is actually we have to move towards the efficient power consumption. Then scalability and deployment. Again, since we have having the number of elements and if we want to increase the number of users, so similarly the elements of the RIS needs to be increased, which actually again enhances your interference problems. So that has to be concatenated with each other. And the last one is the security, which we already discussed with you. So thank you. And
question for the student.
Yes.
5 questions for the student. Please ask question. Yeah.
we are going for the full duplexing mode, especially in the OFDM. So how it will work? So because one side we are transmitting to the other direction and we have also received the signal to the desired direction. How it is going to work?
Actually, for that we also it is simultaneously transmitting and receiving antenna like RAS. Where there we can have your RAS. It can work under 3 different modes, like 300 different modes. One is your mode switching, then second is your time switching, the third one is your energy switching. So this mode switching can be utilized for this OFDM case, where it can be used for different modes, for different uses.
Next question. Be bold and ask question. Show your courage. I want the courage from NIT. Yesterday I had a meeting with the director. The director told me that the students are very bright.
Yes.
But now show your brightness. Ask a question. Anyone? Ask one question to this young boy.
How much maximum elements we can include in this IRS? What should be the limit? As the element increases, the requirements also increase.
Actually,
Meanwhile, I am ordering the Bangladesh student get ready to ask one question.
Actually, there is no such massive MIMO. So for those massive MIMO, we also require a large number of elements. And depending upon these application scenarios, this number of elements can also be configured. But actually, it has to be increased in the 2 to the power of n. It's a case.
Can we keep, say, infinite number of elements? It should be in 2 to the power n. Can we do that?
No, sir.
Then what are the problems that she was?
We already discussed some of the problems such as your hardware and power consumption. If we increase the number of elements, so considering them as passive will be difficult, because as we increase the number of elements, so the power consumption will be also increased.
But
and other thing is your interference also.
IRS is having passive components, no?
Yes,
So
sir.
where the power consumption is be applicable?
Actually, so the issue is that considering the passive introduces the challenges of channel estimation. So for that, the research works actually what they are doing, they are using some elements like if we have for example, if you have 64 elements in your RIS, what they are doing, they are using 16 active components. So those 16 active elements are used to send the palette signals and all, and to get to estimate the channel.
So it is not having all component as passive.
Yes, exactly.
It is having some component.
Some components and passive.
Very good. Now the question from Bangladesh. Be bold and ask question.
The security purpose of this IRS system introduced in networks.
Security. See, again, if we are providing a massive connectivity, so there is a difficulty in accessing the privacy keys, actually privacy tokens. So sometimes what happens, your eavesdropper can be present near you, and even the legitimate nodes do not know that. This issue actually exists. There are 2 different types of eavesdroppers. Actually, if you know about you can go through the concepts of the security. And this eavesdroppers can be considered 2 different eavesdroppers. One is an active eavesdropper, and the second is a passive eavesdropper. The active eavesdroppers actually it sends it does it actually like wiretaps, or it actually grabs some information, and then it sends that signal to one of its server. So, but the problem with the passive eavesdropper is that it doesn't send any signal. So it actually captures the signal, holds with itself. So that's a problem with the passive eavesdropper, and it's very difficult to observe. It's very difficult to actually discriminate between the legitimate nodes and the passive.
You can mention about open nature of wireless
Yes, exactly.
transmission. So
That's
if
also
any transmitter is transmitting, anyone can receive the signal. So if we don't have any security mechanism, we will not be able to transmit information.
Very good, Gaurav. Well done. Who is the third speaker?
थर्ड वाला नहीं आया सर.
That one, yeah.
रेडी है?
Yes. The bright. बूढ़ा हो गए लेकिन जवानी याद है हमारा अपना, इसलिए जाओ कहाँ छिप के बैठा हुआ नहीं रहता। कल से तुम्हारा चल रहा है 15 मिनट में तैयार होने के लिए। बेटा
So very well, so very warm welcome to regards to my everyone present here, to my professor, Professor Dr. Ramji Prasad, and my teachers, professors, and my fellow colleagues who are present here today. Today my topic for presentation is exploring the 5 senses of wireless communication. And if I speak about my
I love
background,
this topic. Very good topic of my choice. Go ahead.
so I am talking about my background. I am from National Forensic Sciences University, and today my topic for presentation is exploring the 5 senses of wireless communication. And special thanks to Mr. Aditya Mohan Srivastav and Kartikeya Mishra for helping me to prepare the slides.
So they have prepared your slide.
No, I have also prepared the slides. They also have helped me in the research process. So, I will start with the traditional wireless communication. Traditional wireless communication, we have sight and audio, which is there in the 5 senses of communication, which right now we have, which are discovered. So actually the whole topic for the communication or the whole human bond communication, I took this from research paper which I found it on the internet after I based it. The research paper was published by Professor Ramji Prasad himself. So the whole presentation I took it from there, and human bond communication, which integrates 5 senses of communication.
Prepared your slides with my paper. 15 years before, I think.
Yes, I took some help from that also.
You have to pay something.
Yes. So I took the help of your research paper also. So the 5 senses of communication, here we can see the sight, hearing, smell, taste and touch. So the as I mentioned, the human bond communication, here we can see that inducer distributed human bond sensorium and other factors which are here, which are necessary for olfactory, gustatory and tactile interpreters, for which we can deduct and which we can sense for the audio and video sense of recognition. So if I talk about digital and human experiences, so there are basically 5 senses of communication, maybe for eyes, ears, nose, smell and touch. So which provides us an enhanced communication and helps us to provide an distributed network and for basic understanding of communication which is going around us, totally around us. So there are basically 2 types of sensing modalities. One is wave-based sensing and another is particle-based sensing. So what is wave-based sensing? In wave-based sensing, we basically talk about the wave nature, and with the help of wave nature, how we can communicate. So in wave-based nature, we have optical and auditory. Optical and auditory, in the sense we can transfer or transmit the senses of communication with them using the electromagnetic waves. So as I can say that we can store them in case of any electromagnetic waves, and later on recognize them through the waves and distribute them in case of them. And another is the particle-based sensing, which is right now in also another topic for research, which is right now not yet so much of research as of right now. I research which includes smell, taste and touch, requires molecular interaction. So it is a very bright topic to research, which the basic challenges for there is proximity, material replication and accurate transmission. So the accurate transmission regarding the particle-based sensing is very severe. So accurate transmission is not right now, it is not possible for particle-based sensing. So smell, taste and touch is right now for particle-based sensing is not present. So in sensing modalities, we have wave-based sensing and particle-based sensing. In wave-based sensing, we capture the sight and hearing and convert them to digital formats, and we can store them. But in particle-based sensing, we include smell, taste, and touch. So, and the challenges we face there is proximity issues, material replication, and accurate transmission of difficulties. So there we are facing challenges, and here it is another major research topic for the particle-based sensing. Here there can be many research which can be done. If anyone is interested, they can go for it. So I start with the sight, which is the optic, which basic function starts with the color, brightness, contrast, and depth motion. So it is basically what we see, what we store, and how we can store what we see in that through communication. So human eye processes basically electromagnetic waves ranging from 400 nanometer to 700 nanometer range of. So retina, which contains photoreceptors, rods, and low light vision codes for detection. So these are the some topics for sight optics. And optic nerves transmit signals to the brain for image interpretation. So for image interpretation for eyes, which you can see, so we can store them in image interpretation. So how the conversion technology works. So for conversion technology, we can use from basic lens and some CMOS cameras. So CMOS basically stands for converted mechanical. I currently forgot the CMOS program. So okay, cameras and optical sensors convert light into digital images using CMOS and CCDs and lighter depth. So capture 3D. After capturing 3D, we have basically sir told us about AR and VR, augmented reality and virtual reality, how we can store them and how we can feel what we can see. So without being present at that topic, we can be feeling what is going on in the surroundings. And here how it works, sensor functions. First of all, the photoelectric conversion is happening, and then the charge accumulation. The charge accumulation is done in the image sensor, and then it is transported to the ISP. There the transfer signal works, moves to the charge to detection node, and then the signal detection. For the analog to digital conversion, the ACD is used. So the ACD basic function is to convert the analog signal to digital signal and store it, and for the basic human preservation and image data conversion. And next we have is hearing, auditory, sound for wireless communication, which captures sound waves, and then we include speech, music, and environmental sounds which we can hear and store them, and with the use of basic wireless communication we can transport or transmit them to basic mechanism using the eardrum mechanism, which for human range, which is 20 hertz to 20,000 kilohertz for human range, medication range. And if I talk about the basic mechanism of human ear, so the ear, what happens is when we the ear sound travels to the pinna, the basic opening in the ear, then it travels to the eardrum, and then it vibrates in the creating some signals in the cochlea. So the cochlea hair cells convert the vibrations into electrical signals, which then are transmitted to the brain for further communication and for further understanding of the signals which are being transmitted to the brain. And then we have a conversion technology which is here. So how the conversion technology is there? So we can take the basic example of the microphone which is here in my hand, which captures the sound and converts it to electrical signals, and then everyone can hear it on the in the speakers itself. And then speech recognition and 3D spatial audio, and which helps in communication, emotional recognition, and other spatial awareness. So the role of HPC in auditory is that which enables voice recognition, spatial in VR, AR, and AI-driven real-time voice transmission, which helps in natural speech recognition and voice synthesis. So here we can see how it works. Analog signal first of all is taken as the sample, and then captured sample data vibrates to the quantized, and then the quantized sample data is then digitally stored using the digital signal, or here encoded using the where I previously mentioned, the sound is transmitted into electrical signals, and then it is stored as the digital signal. So next if I go, real world examples. Some, as I mentioned, the use of sound, immersive audio, and voice communication, spatial awareness in VR, AI translation, and microphones and eardrum, which I mentioned, biological mechanism which is present. And the smell. So the smell, which is basic thing of human need, the role of scent in HBC, the human based communication. The function of smell is that the chemical compounds which are present in the air helps the perception of food danger and strongly linked to the memory. So once the smell is transmitted or smell is present inside someone, we cannot basically just store the smell. Right now we don't have the ability to store the smell as the olfactory nerves, but we can enhance it using VR and digital storytelling and telemedicine with scent cues. So which helps in remote training for chefs on perfumes and hazardous environment simulations. If we go into the mechanism, we can see that nasal receptors, which is present inside obviously the nose, bind to airborne molecules, sending signals to the olfactory bulb inside the brain. The olfactory system connects directly to the limbic system, affecting emotions and memories. So which is there in the diagram which is shown. Then if I move on to the smell olfactory real world examples, field VR mask simulates scents in VR environments and challenges. So if I talk about challenges, chemical sampling, digital scent encoding, electronic nose conversion for scent synthesizers, and NEC olfactory communication, developing digital scent transmission methods for smell olfactory in HBC. Taste. So taste or the gustatory digitalizing flavors. So the function of taste in human is that we basically what we eat, can we store that, can we preserve, or can we tell anything what we ate last night? If I ate some dal, how the dal tastes, so if I want to tell someone the dal tastes bitter, the dal tastes sour, the dal tastes spicy, how I can communicate to him. So how the tongue tastes, the tongue basically captures the taste of the functions are that it detects the sweet, sour, salty, bitter, and umami flavors through taste bud receptors, which is present basically in the tongue, which is there, which can be seen in the taste buds, and works with the olfactory system, enhance food perception mechanism, and tongue receptors interact with the food molecules, sending signals to the brain, and then thereafter sending signals to the brain about the taste of the food which we just consumed. And then the basic challenges in the technology of the olfactory system is that the molecular recreation and the precision of the taste transmission is basically very difficult to reproduce. So the need for universal taste and encoding standard is basically required in places like digital and audio, which is present already. So basically here, if I talk about the conversion technology of digital taste interfaces, here we can see that uses of electrical stimulation to mimic taste sensations and electrode-based tongue sensors. So this was the small work which was done in the University of Meiji for real-world example, which is also known as the Norimaki synthesizer, a device that tricks the tongue into perceiving different flavors. So basically what this device does is, if I taste something, the device will automatically convert the taste into something else. Maybe the bitterness will convert into any other sourness or anything else. And the taste buds technologies and challenges which I basically talked about is the molecular recreation, which is hard, and the universal taste encoding, which is not present, but which is present in audio and video, which is there. And the mechanism is basically the tongue receptors, and from the signals it sends to the brain. In the real world example, which is present in the Meiji University, the Norimaki synthesizer, and the remote food tasting and functions which are there, which I mentioned. Right. So next and most fifth one is that the touch. So touch and tactile, the power of physical interaction. So the function detects the texture, pressure and temperature and pain through skin receptors. Essential for fine motors and object recognition and emotional bonding. So how the touch works. The mechanism is that through the mechanoreceptors detect the pressure and vibration. The thermoreceptors also for the temperature controlling and the understanding of the temperature, which is around the surrounding, sense of heat or maybe cold. And the nociceptors respond to pain or stimuli to the body. And the challenges to the technology, which may be the touch, tactile, the power of physical interaction. So basic challenges may be recreating the tactile sensations. So basically, if anyone touches me, how will I forward the communication, forward the basically my sense of humor, my sense of communication to him, that he touched me in the here, and so you need to understand how he touched me. So basically, if he touches you, you should understand that it is his finger and it is he himself. So how can you understand? So right now, the complex tactile sensation, grip force, textures and resistance can be developed to provide some basic understanding of that touch. So need for high resolution haptic feedback for realistic interaction is mandatory for the touch sensation to be understood. Touch tactile continuation. Conversion in technology. Haptic feedbacks. Simulate touch using vibrations and pressure. Force feedback controllers provide resistance for a more realistic experience, or maybe soft robotic and e-skin, providing a lab environment for skin, and mimic the human touch for a human using the AR, augmented or virtual reality. And the real world examples which may be present is provide realistic touch feedback in virtual reality and use ultrasonic sound waves to create touch sensations without physical contact. And a full body haptic suit for virtual reality applications. And so the HBC system components, human bond sensorium components, are inducers which convert sensory inputs into electrical signals. And HBS, human bond sensorium, manages secure sensory data processing. And HPT, human perceivable transposer, reconstructs sensory experiences using basic communication.